All right, let me give this a sing. Sweet. Welcome to the Monkey Dance Podcast. This is Ohan, and today I'm sitting here with Niraj.
Hello, thanks for inviting me, Ohan. My name is Niraj Kushwaha, and I'm a PhD candidate at the Complexity Science Hub and University of Vienna. And let me give a bit overview of the things that I do currently, and then we can dive deeper into it as we progress. So my background is in physics, and right now I'm doing my PhD in physics. And in particular, I'm interested in physics of complex systems. And in a nutshell, in this field, what we do is we try to understand how different interacting units can come together, interact together, and result in some emergent behavior, emergent phenomena, or some emergent patterns that we see. So all around in nature, we see it everywhere. For example, flocking of birds is one of the examples. The individual birds making their own decision, but finally you get this huge pattern of these flocks together. Same with people, individual people making their own decisions while walking in a crowd, but then you get this pedestrian dynamics emerging out of it. Same you see in nature, in forest fires. When seemingly forest fires look like these random events that are happening, and then some forest fire result into a big event, some into a small. But if you look at the statistics that come out of it, if the sizes of this forest fires, they show a very striking pattern. Same in earthquakes, etc. So one of the systems that is it's been well documented that it contains these nice emergent behaviors or emergent patterns is armed conflicts and wars. And even though it has been documented that they contain these patterns, it's not well studied how these patterns emerge and what could be consequences of these patterns. So, for example, famously in 1960, Richardson showed that when you plot the conflict intensity, which he measured in terms of the number of people who died, the casualty that happen in conflicts, it show a very striking statistical pattern. So you can plot in a straight line what would be the number of conflicts which have a specific number of specific number of deaths, and it just follows a very straight line. So it tells us if conflict is completely random, you should not get this kind of statistical patterns, but we do see it. And there have been more works exploring this pattern, and they have shown that this appears in data, but no one understands why it happens. So that was kind of my starting point of trying to understand the emergence of these patterns in this specific complex systems, which is of armed conflicts and wars. So,
sorry, can I interrupt you to just explain that
yeah.
one point?
Yeah.
So you're saying that as the casualties rise, what else rises?
Okay. Let me explain it a bit more clearly. So it's a simple relationship. Let's say you have an x and y axis. On the x-axis, you plot the number of deaths, and on the y-axis, you plot the number of conflicts that have resulted in that number of deaths.
Oh wow! Okay.
And so
you have more conflicts that resulted in more deaths.
No, but the
it's inverted.
It's inverted.
Okay, yes.
It's
Okay, good.
Exactly.
Great.
But there's an inverse law.
Yes.
And so there's a lot of conflicts with small number of deaths.
Yes.
And few with large, but they all follow in one straight line.
That's interesting.
Which was
Yeah.
very surprising thing to find.
Yep.
At Richardson's time in 1960s, the data was not as much, so people kind of questioned it a bit. But now with the new data, also we see similar patterns emerging. That's the kind of question we want to develop to understand why this is happening, what's going on in there. And as we embark in this journey to understand this, one of the first demons that we face is right at step 0, which is what is an armed conflict? Which, I mean, it might sound like a trivial question, but it's not. You ask any different experts, they will have their own definition of armed conflict. Now, if you want to build a mathematical model or mathematical theory or trying to understand what a conflict is, you really need to you need to first know what the object of study is in order to first model it. So we started thinking about let's go back. Let's try to identify that first, and then we can move forward. So we started with the fact that fundamentally every conflict is just the aggregate of individual conflict events. So there are conflict events such as a bomb blast is one conflict event, fight between two armed groups is another conflict event, and usually experts aggregate them together and call them, this is a civil war, this is a whatever war. So there are many different narrative or subjective notions people can use, well informed but still subjective notion people can use to form these aggregates of conflict. So we said, let's collect this data. Let's get this data of individual conflict events, which is publicly available. You can go and get it. It's very fine-grained, nice data set starting from 1997 till present day. They track in real time. And we said, let's find statistically if we can identify which conflict events are statistically related to other conflict events. So we developed a method or algorithm to able to do that. So from that, we can tell conflicts even started here. Because of that, a conflict statistically, another conflict event happened here, etc. And if you trace back in time, you can form these chains of related conflict events all across. So we did it in Africa, all across Africa. And we can go deeper into this, but what we call these chains of related conflict events is conflict avalanches. And there's a reason behind it. We call it that because they show similar statistical properties as we see in snow avalanches, forest fire avalanches, etc., etc. And it's the inverse relationship that I told you about. In physics, we call it power law distributions, but we don't have to go into the details. So we found many other interesting things in the research. One of the things we found is the scale at which we look at conflict is very important. So there are some individual conflict events that happen in a place. You can study those individual conflict events at the level of localities, why that happen in localities, at the level of the districts, at the level of the country, at the level of geopolitics, etc. So how can you systematically move between these different scales was one of our other questions which we explored, and we found that there exists a mesoscale. So what it means in simpler terms is that I like to take this analogy is that if we have a microscope and we're looking at armed conflict through a microscope, it kind of tells us that there is a scale of resolution at which conflict starts to show interesting behavior or interesting patterns, this emergence of these power law distributions, etc., that I talked about. So it's like if you look from very far away, everything is blurred. So it will look like all the conflicts that are happening in Africa are all one giant conflict. If you go too down into it, each conflict event will be like an individual conflict. It's happening on its own. But if it's just enough level of coarse graining or blurring, then you start to see these interesting patterns. So that was one of the first things we did. And then once we answered this question, how do you define a conflict in a systematic fashion using purely data and the statistics of it, our next question was how many types of conflict exist. So in literature, people relate a lot of different data sets, like they study conflicts with respect to a lot of different data sets such as GDP. What's the geographical condition of a place? What's the infrastructural condition of a place? And how did that affect the conflict at that place? So we said, let's combine all these data sets. So we collected around 21 different data sets and build this massive hyper data set, you may say. And we wanted to see if there are some systematic conflict types that emerge directly from data without giving any of our information or our biases. And what we found was that at every scale that we look at, every spatial and temporal scale, there emerges three main archetypes of conflicts purely from data. So it can tell us how many different conflict appears in different kinds of conditions, basically conditions such as geography, climate, democracy, different democratic compositions, etc. So that was one of the cool findings. But then another thing that the main question we wanted to get at was that can, using all this information that we have, can we actually predict anything about conflicts? And that's one of the things that in the field people are doing a lot. They're building a lot of machine learning models and deep learning models, and trying to achieve prediction of what eventual intensity of a conflict will be given certain conditions. And what we show is that that's actually not possible. So you can measure something called mutual information, which tells us how much information one variable contains about this other variable. And when we did this analysis, what we found that there isn't much information between these different variables to be able to extract anything. So whenever you apply a machine learning algorithm, it just kind of taps into this mutual information that these variables have. But so this mutual information kind of gives you like a theoretical limit of how well you can do. And we see that theoretical limit is not that high. So we're kind of trying to nudge people away from this approach and trying to, like, it's not worthwhile to use, try to build a model which will suddenly predict everything about a conflict. Rather, it has to be very context-driven research that you need to do. So yeah, that's like a general overview of how, as a physicist, I'm trying to approach these questions and go into this.
Yeah, let's go actually right back to the beginning when you talk about types of conflict, right? Because, yeah, presumably you could have a situation where some conflict is going on, but then somebody randomly goes with a gun and shoots a couple of people in a town. And you don't want to count that as a conflict because maybe it's unrelated, maybe it's a personal dispute. So how are you personally defining conflict? And maybe how are some of the other ways that people define conflict? Why don't you use those?
Yeah. So here, whenever I'm talking about conflict, I'm talking about this chain of conflict events that we discovered from the data itself. So the conflict avalanches. So we're only talking about in terms of these systematic definitions, which we can use to model and try to predict anything. We're not talking about like specific narrative-driven or expert-driven conflict types, which are very useful, but not for this purpose. That's why we want to separate these out. Why? And there are some tests, like we did some tests to see if these statistical pattern that we do get does actually correspond to what's happening in ground. If it's not, there's all of this is gone. There's no need to do this. This is just stupid. But we found that it actually gives a lot of great information. I can give you one good example. So if we look at conflict in Nigeria, in the northeastern part of Nigeria, there's this Boko Haram insurgency that's going on. In the same region around the periphery, there's another conflict called Fulani conflict that's going on. Fundamentally, these are two different conflicts. Boko Haram is an insurgency, it's an insurgent group. Fulani conflict is a conflict between herders and farmers in the region. And usually when people study that, if you're trying to build any mathematical model and try to study mathematically, do some correlation analysis or anything, either people group all the conflict events in Nigeria as one big chunk, so everything is related to everything basically, or they separate out, this is Boko Haram, this is Fulani, these are two different chunks. What we found in our algorithm, when we do that, when we look at statistically, there are some conflict events, Fulani conflict events, which are statistically related to the Boko Haram conflict event. That's what we got in our algorithm. So we were initially puzzled, but then we looked through the literature, and what we found was that in that region, when people went on ground and studied the place, what they found was that when Boko Haram increases their attacks, the Fulani herders have to flee the area, they go to a new area, and there's more conflict over there. So there is this causal relationship between these events, which we were able to identify from this just purely by looking at data. So this statistical pattern has a lot of weights. Similar examples we found in Somalia, etc., etc. So now we can't go everywhere on Earth and find each and every what's happening each and every place. So these kind of methods can complement that qualitative research. It's not a replacement for it. It would complement that, and it can kind of give you an insight of where to look and what to look at. Similarly, at Sierra Leone, usually there was some allegations made that there are some people coming from across the border and trying to inflict conflict. and conflict that are happening across the border has resulted some conflict over here, and people were denying it. But again, through this analysis, we do see that there is some causality. Now, it could be true, it could be, but it kind of gives you an insight. Okay, go there, look at this specific place, investigate this specific conflict event. And so yeah, that's why, like, it's a complement, as I said. That's why in all our analysis, we're just using the conflict avalanche definition. And when I said the conflict types, these are the types of conflict avalanches that we get from data. So basically saying in the end that, okay, if you're building a model for conflict, you're trying to build how a conflict spreads or how whatever happens, don't model it on conflict aggregates based on countries or cities, etc. Instead, try to build a model on this conflict avalanches. How does this conflict avalanche spread? And there cannot be one model that explains all the conflict avalanches or conflicts. There has to be at least 3. And even in this 3, what we found that there is a taxonomy of conflict types. So there's 3 main archetypes, and which bifurcates into way more. So there could be 3 main models or theories, and there could be like a segregation around. So that's what we're doing.
Yeah, really cool. So I guess my next question is going to be, can you walk us through the 3 types?
Mm-hmm.
But I guess just to give you another second is so basically what you're saying is that this isn't what confirms hypotheses. This is actually evidence so that you might be able to generate new hypotheses and then go on the ground and then see if these hypotheses are true.
Yeah.
Right.
Yeah, exactly. This is like looking at data. Where does the statistical information reside? It's again, as I said, it's a complement to that. Now, coming to your first point, you want to know about the 3 conflict types. So we found there are 3. One we call major unrest. Second, we call local conflicts. And third, sporadic / spillovers. So we found that in Africa, from 1997 till present day, all the conflict which lasts from maybe 1 year to multiple years and has the tendency to spread across a country's boundaries, those conflicts naturally cluster together, and they all are part of this one conflict cluster called major unrest. That's what we call it, major unrest. All the conflicts which last from few months to maybe a year and usually reside within a country's boundary, they are all part of local conflicts. So usually the civil wars of a country, they were part of this local conflict cluster. And in the major unrest, the Boko Haram and the Al-Shabaab, they were in the major unrest cluster. And the third is sporadic spillover. So conflicts that just start and fizzle out, and they are very local in nature. They all naturally cluster together. And also, so those are sporadic, but there's also spillover conflicts, which are together in the same cluster. Spillover, one example is in Somalia, there's the big Al-Shabaab insurgency. But if you go to the north, in the Bosaso region, there's a lot of other insurgents which are inspired by the Al-Shabaab insurgency, and they have their own conflict going on there. So they're like a spillover conflict of the Al-Shabaab insurgency. So they all naturally cluster into these 3. So these were the 3 main types. And not only knowing the type, we can also know what kind of properties these conflicts have. So the major unrests have the property of, they usually happen in regions which have high population density, good infrastructure, and good to medium economy. And they're around riparian regions. So geographically, they're around some kind of water bodies. Local conflicts happen in regions which have medium population density, good to medium infrastructure, and etc. There are a few other, in terms of there are a few other parameters. And sporadic spillover usually happens in remote areas where low population density, their infrastructure is not good. So usually the conflict starts and then fizzle out. It doesn't spread into other regions. So these were the properties of the 3.
So the Fulani conflict with the farmers, this is a local conflict, or is it because it's based on resources, this can also spill over?
It can spill over, it can go, but in our algorithm, we didn't get a separate Fulani conflict and a Boko Haram conflict. We got this big cluster,
Gotcha.
Which is a mix of Boko Haram and Fulani in that region. Then there are some other events that are completely Fulani, which are separately Fulani. So usually the bigger cluster, the Boko Haram cluster, that's in the major unrest. because that can spread over, that crosses a country's boundaries, etc., etc. And lasts long. The Fulani is more like a local conflict. It stays in the local conflict cluster. It stays. It does cross a little bit of border because the borders there are quite porous, but not too long. It's kind of spread. It stays in that region itself.
Right. And you have a situation where on the border region between Nigeria and Cameroon. So what does that type of separatist movement constitute?
Yeah, that went into the local conflict cluster. So because it stays near the border and doesn't grow beyond. It's just concentrated there. So that in our algorithm, it went to the local conflict cluster. In Nigeria, there's another interesting part is so usually if you look at data-driven studies of conflict, as I said, there are some heuristics people use. Either the whole country is one, they all combine all the conflict events in the whole country as one, or based on cities, or based on actors, so Boko Haram, Fulani, etc. But if you look at a lot of qualitative studies done by experts, political scientists there, they say that Nigeria is going through, or at some point was going through, this triangle of terror. So there are these three main epicenters of conflicts that's going on, and they have their own mechanisms, and they should be studied separately. That's what they've been saying. Once we did this statistical causal study, we retrieved this three triangle. So there was this Boko Haram cluster, the Cameroon one that you said, at the border down here, and on the western side there's a lot of rebel activity, but it's like local rebel. They're just fighting for resources, and therefore there's a lot of loot and things like that. So that's a separate conflict. So these are three different kinds of conflicts that's going on in Nigeria that you can just get out from data itself if you just don't put any of your biases in there. So yeah, that's
right on. And I guess one more question about the type specifically is when you discuss Al-Shabaab and then almost these sympathetic or copycat movements, they're related because they actually have communication, or simply because one inspires the other? That's enough to kind of cluster them together.
Yeah, I mean, this is a question more for the political scientists and who can go. I can say from the physical and data side of what we are seeing. I know about this Bosaso example. In that case, there has been reports that there is communication, and that's why there's their own thing that's going on. It's quite intense in the north. They fight a lot. But again, we can only, unless we go on the ground just by looking at data, we cannot say these things. We can just look at these patterns, and we can see what kind of interesting phenomena emerges from it. So, as I said, the Richardson law and the power law distributions. If you look at the avalanche sizes, we get the exact same thing. You get the exact same power law in number of deaths, duration, etc., etc. So that's the kind of questions we want to tackle as why these phenomena, which are results of these millions of decisions that are being made by people everywhere, results in emergence of such interesting phenomena. So
yeah, and so whenever you're looking at conflict, one of the main drivers of conflict is control of resources, even land as a resource. And this even is what drives a lot of spillover conflict, is because then resources are constrained, some pipeline is damaged. So do you account for resources in the modeling? Is it purely interaction and conflict?
Yeah, so we could have put resources are one of the data sets in this, but we did not, because we had some strict criteria for what kind of data set we want to include in there. Data set which has fine-grained enough to be part of this analysis. If it's too coarse, then it won't be able to complement the other data sets that we have. Resources or resource fluctuation in a region, unfortunately, is very scarce. However, one can argue that the other data sets, like the geographical conditions, how much water is there, how much rain that happened, what was the temperature in that region, what's the GDP of that region, GDP per capita, these all kind of have, it's kind of like a proxy for how much resources there is. So in these variables itself, there is some information about that. It's just not explicit enough. So yeah, if once we get a data set which is good enough, fine-grained enough to do this, it'll be, yeah, we should add more and more and try to see what comes out of it. But yeah, right now, no. Right now it's more like a, yeah, at a proxy level we can say what's going on in resources.
Yeah, and so can you go a little bit more into the mesoscale? So you're looking at all the data, and there's some intermediate amount of time and space,
Yeah.
right, that you kind of identify as a crucial metric.
Yeah.
So yeah, can you describe the mesoscale itself, and then why it's useful?
Yes.
What does it give us?
Yes. So maybe I'll start this whole discussion with the idea of scale. What do we mean by scale? Why is this necessary? Why are we talking about this? So I'll give you with an example. I'll start with an example. So there are some conflict events in Nigeria. Let's say there are some conflicts in Nigeria, and there are some conflict events in Mali, which is a country neighboring to Nigeria. At one narrative scale, one can say that all the conflict events in Nigeria are part of, let's say, the Boko Haram insurgency, and it's something's going on there. So that's one narrative scale. And at the same narrative scales, which is at the scale of countries, one can say the conflicts in Mali are happening because of the civil war that's going on in Mali. So that's one narrative scale, country-based. Then there's a huge literature and huge discussion about the fact that in the Sahel region of Africa, so this kind of band of countries in Africa, there's a emergence of a major unrest. In this whole region, there's an unrest. And when you talk about that scale, that narrative scale, all these conflict events that happen in Nigeria as well as Mali are part of this main idea of in this unrest that's spreading in the Sahel region. So there are these different narrative scales. If you look deep into it, these narrative scales are nothing but accounting for spatial and temporal scale. Lower spatial scale or higher spatial scale. Lower temporal scale or higher temporal scale. So in our study, because we have this data, we can navigate between these different scales and see what kind of patterns can emerge at each scales. So I'm not going too deep into the kind of metrics we used. We used some information theoretic metric called transfer entropy, etc. It's let's not go there. I mean, I can just very briefly say something like transfer entropy measures statistical causality. It kind of tells you how good you are at predicting something else if you have information about this. So if you have two time series X and Y, if you know the information about X, can you predict something about Y in general? So these are the different scales, and we can titrate between these different scales. What we saw that if you're too big, too high in the scale, you don't get any information. It's just, as I said, every conflict event is connected to each other. Statistically, they're all related to each other. Sure. I mean, we can say that, yes, the world is in chaos. That's the kind of idea that comes out of it. And if you look at these emergent patterns, as I said, you don't get this nice power law or any of this emerging if you look at the size of conflict avalanches at that scale. Now, if you go too deep, each conflict event is its own. It's like saying that, there's no need to do any of this study. Every conflict event has its own context. We should study them completely separately. Sure. But again, if at that level, if you look at the conflict avalanches, related conflict events, they are very small avalanches. You don't get any of this distribution. And so at a very specific range of scales, which is, I forgot the exact values, but it's from few kilometers to around 400 kilometers, and starting from 1 week to around 3 months is where we start to see interesting patterns emerging. If we look at conflict avalanches at that scale, we see this emergence of power law distribution, etc. And it's also there's interesting thing that in the previous research, when people have been doing correlation studies between some climate variable and conflict or infrastructure, and they have found there are a couple of papers. Right now, I remember one where they found that if you group conflict events at the level of 3 months and correlate it with climate or something, you find some signal. You find that they are quite useful. If you go beyond 3 months, you lose the signal. Then there's no correlation there. And in this study, we see that the mesoscale cuts right at the 3 month mark. So it kind of gives you, okay, this is the region where you look at your microscope, you set your microscope within this, where you see different emergence of different interesting phenomena within this scale. And so why it's useful? Well, you're doing a policy research, you're trying to see how you want to allocate resources, you want to study what kind of patterns, how conflict is spreading in a given region. Well, this is where you have to fine-tune your models. You have to fine-tune within this scale. You have to look at this many kilometers, this many months or whatever, weeks, and that's where you will find interesting things to follow up on.
Yeah, that's really cool. That must have been an exciting moment also when you find that.
Oh, yeah.
So when you say after 3 months you get a drop-off, so what does that mean exactly? What does that look like?
I mean, the drop-off, in our case, the drop-off means that you no longer see emergence of any interesting conflict avalanches or any meaningful conflict avalanches. There could be case something like, if you look at scale, if I increase the scale way too much, then Boko Haram conflict events are statistically related to the Al-Shabaab conflict event. It doesn't make sense. They're two separate. Sure, ideologically they're following each other, etc. But yeah, on ground there are like two separate things going on. So the drop off happens in this sense, in that the emergent patterns that we expect to see, the interesting patterns, it suddenly disappears. Like once you go beyond 3 months, it just disappears, and conflicts are just this kind of random processes, or just all coalesced process at those scales. So yeah.
Yeah, that's great. I mean, you have this problem, I guess, across all of science, the crud factor, that everything is mildly correlated to everything else, even if there's no causal chain. So looking at something like, I think transfer entry is a good example, how say the past of something informs the future of something else.
Exactly.
Because in a random situation, you have where the past of Y doesn't inform the future of Y at all.
Yeah.
And then you have some kind of information where the past and future of Y are correlated. But then if information about X impacts Y, then you have something tangible that you can hold on to.
Yeah. That's what you try to extract using this transfer entropy. Another interesting thing about this is, like, as you mentioned, correlation versus this transfer entropy measures on that. We tried to do this whole study with using some correlation metrics to see what happens. And what we saw is that they were unable to extract useful statistical information. Again, it would just give all kinds of this related to this. It will give that conflict events in Boko Haram somehow gave rise to insurgents or something, some civil war in Egypt or something like the correlation was not at all a good metric to do this kind of study. You need really strict filtering mechanisms, some really strict statistical filtering mechanism, which is this transfer entropy, as you said, which gives you this kind of this idea or insight into what lies there in the statistics of it. And another great thing, as you mentioned, transfer entropy, is that it's bidirectional in nature. So usually correlations are unidirectional. So X correlates to Y, so Y also correlates to X. But transfer entropy kind of gives you, you can get information such as X impacts Y, but Y doesn't impact X. So there's only unidirectional relationship, and it kind of gives you how strong that is, etc. So using this, you can form really robust chains of conflict. So a conflict starts here, it can go here, but conflict from here cannot go back to there. So it's situations like this, which actually we do see happening in real world. So a big conflict that starts in the city can go into the villages. Usually the conflict from villages don't get to the city. So that kind of filtering can happen with transfer entropy.
So maybe we can also make it a little bit more concrete in terms of the steps that you actually take to do this type of analysis. If we look at, say, to use an example right now of Sudan, and then spillover conflict in South Sudan. So if you want to try to understand or provide some data, actually help people who are going to go on the ground and try to understand what's going on, what do you actually do? So,
okay, I can run through the analysis a bit. So We have data from ACLID, so Armed Conflict Location and Event Database. It's a free database out there. They have individual conflict events that they collect from news articles from international and local everywhere. One great thing about them is that they never use any automated scripts or any web crawlers or anything. So they have vowed, at least for now, to use human experts.
Wow.
And yeah, for every country, everywhere they have human experts. They look at the news articles and then put in the data set. And they keep refreshing too. So let's say there's some new information that instead of 10 people, there were 20 died. So they will update it in the data set, and it's real time. So it's pretty good, very fine-grained, very at the fundamental level of what's happening on the ground. And so we have this data. Let's say you said Sudan. Then what we do is first we have to set a spatial scale at which we want to do the analysis. And we cover all of the Sudan in this Voronoi grids. So Voronoi grids are these pseudo-random grids that you can generate. What this effectively does is it gets rid of all the biases that can come from borders of a country or any administrative border in general. And this also gives us this advantage of you can generate a lot of different variations of these Voronoi grids, and you can do an actual statistics. So this grid itself doesn't bring in any bias. It kind of ensures that, which is also one of the things that should be done. Like in literature, people do use grids for a lot of study, but usually they use square grids or rectangle grids, which are easier to make, but then again, they're a bit too rigid. Voronoi grids give you this advantage of it's a very random grid with average distance kind of fixed, which is the scale. So you do that for each Voronoi grid. Now you have a time series of conflict events. And from this, you can measure transfer entropy. And if let's say there's two regions, X and Y. If the transfer entropy is significant between X and Y, what it means that a conflict, if a conflict happened in X, it can potentially trigger a conflict in Y. But not the other way around. It has to be the other way. Like if it's bidirectional, then the other way around. And now we can get this kind of causal network in that region. So it kind of tells you what's the spatial substrate on which conflict travel. So if your conflict triggers at one location, it will go in X number of distance and not everywhere. So this can also help you in, let's say, resource allocation. Let's say you start a conflict emerging at a location X by looking at this kind of causal network of that region. You can say where you should put your resources to. Where's the probability of this conflict spreading more in that region? And again, in this discussion, when I'm saying causal network, it's a statistical causality. It's not actual causality. Okay. Let's be clear. It confuses a lot of people. And yeah, from once you have this network, now you can build chains of related conflict events. You can look at conflict events which happened in two cells which are connected by one of these links that happen within a specific time period. And you can then say that these two conflict events are statistically related to each other. And that's how you get these conflict events.
So real quick, so are you putting the grids on top of a map, and then you extract the causal relationships, and you can repeat this thousands of times?
Yes.
And then you just kind of average out what the relationships are?
Exactly.
Cool.
Yeah. Yep. You can see, if you do this thousands of times, you can see which of these links are actually statistically significant. Right. And then just came out of like random fluctuations. And that's how we get this really robust conflict avalanches. And you can say, okay, this avalanche actually does exist. This also allows us, if you want to go more technical, this also allows us to get a value of what's the probability that a given conflict event is related to the conflict events. So we're not just saying that, it's related to each other. No, we say there's 75% probability that they are two related to each other. So for example, going back to the Boko Haram example, in the main center of the conflict, all the conflict events have probability of 1 of being related to each other. They are definitely related to each other. But at the periphery, you see that this probability starts to drop a bit. It goes till 50% to 60% or something, and the Fulani militia conflict events it's around 50 to 75%, something like that. So it gives this uncertainty too in our modeling, which is great. It can also be if you're building a policy. If you're using this kind of modeling to build some policies, you can in the back of your mind you can have this uncertainty, like how much you're certain things are happening the way you think they're happening. So which is another cool thing about this.
And so presumably if, say you have an outbreak of a disease, you're trying to figure out whether deaths are likely related because it's a contagious disease. Could you use this and then kind of guess, before you actually go on the ground and test if all the people are dying from the same disease?
Yes. Yeah, exactly. So that's a great question. Thanks for asking. So this, when we developed this method, it was not specifically built for armed conflict itself. Any kind of social spreading phenomena can be studied with this exact same methodology that I said. You divide the information you have into these grids, spatial temporal scales, and you measure transfer entropy, and you can kind of see which events are related to each other and by how much. And so that was one of the follow-up work that we were planning to do, is study epidemics or migration in that regards. So how does this migration from one place to another trigger other migration to other places, or vice versa. So yeah, any kind of spreading social phenomena we think can benefit from this analysis.
Wow, this is really cool. So there's also one thought that immediately comes to mind is you can kind of, if you had good survey data on what people believe politically, you could even say understand how much is spreading based on people's location socially versus what's actually going on the internet, right? Like if you actually get like a social spreading correlations based on people's location, then they're also talking and spreading beliefs among themselves offline.
Yes.
Right, that's really cool.
Yeah, but you need two components to this. There's a spatial component, so you have that, but you also need a temporal component.
Yeah.
So the survey has to be temporal in nature. It cannot be like you have this one giant survey of everywhere at one time step and that's it. If you survey the people again and again, and you have spatial and temporal scale, then yes, then you can do this analysis and you can find actually which came first and which potentially triggered the other and what's like how this is happening.
Cool. So you have, surveys that are compiled every year, for example, and then you get something cool that you can look at.
Oh yeah.
Wow, that's really fun.
Yeah, that's all very cool avenues to try these things. I'm looking forward to that. I mean, I have some colleagues I talk to who are interested in applying this to climate data. So climate data is also very fine-grained. So climate data and conflict, climate data and migration. So it's not just you can look at time series of only conflict. It could be climate, conflict, climate, migration. Right. And you can find this kind of statistical relationships and see what is triggering what and at which scale. That could be cool. And other people are trying to do the same for economics, and there was some, I forgot, like share market price, but I don't know if that will work. That's too. And also, I'm not interested in thinking about that. So.
Yeah, seriously.
But yeah, in general, I think there are three main components. It's great that you brought it up. Fine-grained data, spatial component, temporal component. If you have these, you can do this kind of analysis and see what comes out of it. Mm-hmm. It cannot be said, you can't really predict what will come out of this, but it's like a nice curiosity-driven research. You just go in and see.
And so I know that there's one sort of branch of complexity science that looks at how civilizations rise and fall, right? So to me, I guess I'm sure the people working on this think about it the same way, is that that's kind of a repercussion of so many factors, right? And it seems like the things that you're targeting, especially with conflict, but then also potentially climate change, migration, are actually what contributes the stability of a particular state, right? And so is that kind of the main emergent factor that you see from this type of work? Like you can probably predict the stability of even borders if you're looking at something like, a mix of conflict and migration and climate.
Yeah.
Does that make sense to you? Or
It makes, yeah, as far as I understand, that's an interesting question. However, I have two objections to this.
nice. Okay.
So one is all this analysis. I mean, if we go a bit more into the physics side of these things, seeing the emergence of this distribution, power distribution, this avalanches, etc., kind of points towards a thing called self-organized criticality. It's a theory from physics, which people usually study in regards to forest fires. When they say forest fire are a system which remain in the self-organized critical state. The brain activity, they look at neural avalanches and they say they are at a self-organized critical state. And basically what self-organized criticality or SOC means is that a system wants to be near the critical point. So whenever you try to push it forward, it kind of relaxes, comes a bit back, and then this loops kind of keeps repeating itself.
It's almost like homeostatic.
Yeah. I mean, it's like this kind of things then results in these avalanches. So one great example is this sand pile experiment. When you have a sand pile and you keep dropping sand on the top, you see that the sand pile's angle kind of keeps getting narrower and narrower, and then it goes down, and that results in avalanches, and it relaxes by making avalanches. Now these avalanches can be of any size. It could be a very small avalanche, or it could be like a big one that happens. Same happens on the snowy mountains. And same in earthquakes. Earthquakes are also, the plates are in a self-organized critical state. That's what people say, and that's why we get this earthquakes of different sizes, which follow this nice regular law, the Richardson-Gutenberg law. Now, the difficult point is, since if these systems are indeed near this critical point, it's impossible to predict what will happen to it. In physics, if anything is near the critical point, you can only look at the distribution. You'll find this nice regular patterns. You can make predictions such as there would be this X number of this big avalanches. For example, people can make prediction in the next 100 years we'll get 3 9-pointer earthquakes or something. But you can never predict things like, oh, the next earthquake that's going to happen is going to be this. It's going to be this scale, even though the plates are the critical state. So therefore, if a system is indeed at a critical state, you can never make the next prediction. You can only give this like a range of things that they follow this organized like law. Now, if, as you said, the stability of borders of civilizations, if indeed these systems are at this self-organized critical state, which from the work that we did with the armed conflicts, it points towards it, that it is. Proving it would be very difficult for any real system. It would be very difficult to prove this. But indeed, if they are, it would be pretty damn hard to actually predict, okay, the next conflict, this border is gonna go, and there's gonna be a new border emerging or something. We can make predictions such as in the next 100 years, if the system stays like this, there could be X number of big conflicts emerging, or X number of this amount of conflict, this intensity of conflict emerging. If the system is at that state itself. Now, there are ways to maybe drive that system away from that critical point so that you can kind of build your society in a way that it's away from that critical point. You can have some peace initiative and things like that. And so therefore this can break, and then the probability of seeing these big conflicts lowers down. But again, we can't say. So this proper prediction thing that you mentioned would be very hard if actually our societies live near a critical point in this regard. But the rest of the other things, we can prepare ourselves if something like this happens, how to get ready for it.
Yeah, right on. So you can basically look at the likelihood of a certain set of outcomes within a temporal scale. And so as the dynamics of the situation change, certain outcomes become more or less likely.
Yeah, you can say, yeah, it's a bit murky, but yeah, it's about right, I would say, yes.
Okay. So then because what I'm thinking is if you have an economic situation, for example, due to a number of factors, and you look at how the situation is progressing, you could say it might be better to take steps X, Y, and Z to basically, reinforce the structure, right? Like create a small avalanche that will kind of ease some of the pressure and then retain stability.
Yeah. That's one good interpretation of it, or how things can happen. I agree. Like, I don't know how to, because if you're talking about armed conflict, it becomes a bit tricky because in that sense, we are saying things like, oh, in order to avoid this big conflict, it's better to have these small conflicts, which is not what I
see what you mean. Yeah, I see what you mean.
This is not what I endorse.
Right.
Rather, it would be if the whole system just drives away from the critical point. If it's peaceful enough, it's away from this, the chances of any conflict can be reduced, and therefore this whole thing can break down. This whole avalanche situation can break down. That would be a better better way to tackle this than doing the small conflicts here and there. But again, what are conflicts are again very. Yeah, it's very. Let me think of the thing is in the data set. If ECLE data set, they don't only track the conflict events which are violent in nature, but they also have things like strategic developments. So any diplomatic meeting they had, any new policy that came out that kind of impacts these things, riots, protests, all these things are also encoded in it. So all this armed conflict that I'm talking about has this information too. So in this regard, it'll be like saying, instead of to avoid this big catastrophic conflict, let's have these small conflicts, which are these small agreements and strategic partnerships and things like that here and there, to kind of keep cool down. In that regard, yes, I agree with you, and I can say that, which would be a much better interpretation of this.
Yeah, that's kind of where my mind was going, because then I was thinking, not to kind of keep pulling you out of into different domains, but the way, say, an economist would try to keep balance is, manipulate interest rates, bonds, printing of money. So it's these small things that might be painful in the beginning, but then hopefully they sort of ease the tension and the likelihood of collapse.
Exactly.
Right.
Yeah.
Wow, that's super interesting, because then you also get into things like, how people interpreted the right pandemic response. Some people were like, well, some people need to die for herd immunity. Other people were like, well, we should completely quarantine.
Yeah.
That's super interesting. So then the injection of the vaccine into a population is then sort of this critical event that changes the dynamics.
Yeah. I mean, it drives the system to it really disturbs the system and pulls it out or away from this critical state.
Cool.
Also, like these in terms of epidemics, like this but localized quarantine. Like there were like specifically quarantine this town, this town. Like this kind of small quarantines were also useful that people found. It could also be one of the examples of such a thing. Like instead for preventing the whole system to implode, let's take this small measures here and there, and just make sure it stays intact.
Right. Yeah, which is kind of a similar strategy that you use up and down the scale, because you quarantine an individual in a village, and then you might have to quarantine the whole village, and then you might have to close the borders of a country. Cool. So you have these two great papers out on looking at this model specifically. Is there some more work going on with war and conflict specifically, or is the next work kind of applying to a different domain?
So currently I'm working on my last PhD paper, which is a bit different from this. It's on migration. It's on migration dynamics. It's a simple model that we're like a physics inspired model that we're building to explain different migration dynamics that occur, such as there could be oscillatory dynamics, there could be this bursty dynamics of like there was no migration, suddenly there's a lot of migration, and things like that. So it's a bit away from this. Talking about the future, yes, I have some plans, like if I go for a postdoc to build on these. I'm more interested in building tools using this kind of research that can directly help on the ground. So one of the things that, as I said, like once use of this causal network can be used to identify hotspots, conflict hotspots, and conflict spread hotspots. And in places like Africa, where you have low resources, it's very important to allocate your resources properly. And this can kind of help you identify those places. So things like this, I have this other idea of studying conflicts in regard to democratic backsliding with this professor. That's a big topic because, yeah, it's I mean, we all are seeing democratic backsliding all around the world right now. With that, there's another thing that has emerged, which is interstate conflict, which for a long time was not happening. Like, it was people in the early, I don't know, 90s or whatever, a bit earlier, after the end of Cold War, they really thought that interstate conflicts are done. We're not going to have, we have reached the place where we're going to be fine, everything. But now we're seeing this emergence of democratic backsliding and the emergence of interstate conflict. And so there's some ideas on how to study these, what's the kind of causal relationship exists there. Also, the testing of Kant's democratic peace theory, where he said that if states are democratic in nature, they will not fight each other. And this kind of proves this theory once again, that now that states are becoming less democratic, they're starting to fight with each other again. So these are the kind of directions I want to go in and see how can I help. Like if we can use this bit more physics-inspired methods to study these questions. Yeah, that's my future plan. See.
I love that because also a lot of my sort of work on understanding cognition is also starting to look at things like democratic backsliding, looking at trade-offs, looking at conflict emergence.
I mean, there's a polarization and how people's perceptions has been molded by a lot of things outside. That's also a big part of it. I'm not sure. I don't think I'll be able to go into that. What role social media is playing in creating this divide, polarizing societies, and that resulting in democratic backsliding. Because for democracy in general, you need a cohesion. Like, you need people to be together. If you're away, I don't know, that doesn't really work with the system. So yeah, that's another interesting thing to look forward.
Yeah, and it's interesting because there's so many different ways you can look at it. Like, there are folks, working on the social media aspect, and then you can look at sort of the individual cognition aspect, or you can look at sort of the group dynamics and population level.
Yeah, exactly.
And it's funny because we maybe wouldn't be so focused on this, almost certainly wouldn't be so focused on this if we were doing research in the 90s sort of state of the world, right? But then
exactly. I was having this conversation with the professor I told you about. He's Professor Siereman. He's from ETH as a political scientist, and he said, back in people were super optimistic about the world. They were like, everything is going great. We're having globalization. Let's have more globalization. Everything together. The UN will keep everything in check. And now everything is kind of dwindling. I don't know. So at least from a young person's perspective, I think we need older people to tell us their broad temporal perspective. But from our perspective, that's what I see.
Damn. I don't remember the exact quote, but I remember close to it. George Orwell said, if I was living in different times, I would be a novelist. But given the state of the world, I'm reduced to being a pamphleteer. And it's like, it's... So you have a range of work in physics as well. Before you started working on sort of complexity science, or I guess it was all kind of complexity science, but looking at conflict. Are you okay kind of diving into just a couple of the things to?
Yeah, sure. I mean, I don't remember much exact details, but I can. I think the very start I did during my bachelor's, a bit after my bachelor's, it was like a pure physics. I wanted to be an astrophysicist, so I looked at the radiation that comes from supernovas, the cosmic radiation, and how it bends in the non-uniform magnetic field, and etc. etc. I did some of that calculation. It was very interesting. I wanted to do that, but then I got kind of bored, and I started looking at my other interests, where I was very interested in social sciences, political science, humanities, etc. And then I found this complex systems, which is this combination where physicists, mathematician, everyone else can come together and kind of study these complex systems. And in my master thesis, I worked on complex system of this flocking behavior. As initially I talked about, like when there are different birds, they are doing their own things, but they're also interacting with each other. They can see each other, and based on each other's movement, they're kind of changing their movements, and that results in this huge flock that comes out. Same happens with fireflies. So in fireflies, they are all twinkling, and they all can see each other, and they start to match each other's frequencies, and then they all do it together. In the brain, also the brain stays in this semi-synchronized fashion, all the neurons, but can also get into this. If it's fully synchronized, it's bad because it's epilepsy, basically, and so it stays in this chimeric state. So some of the neurons are always synchronized, some of not. They're in this kind of mixed state, and I wanted to model these kind of phenomena using some oscillators, some physical oscillators. So you can build a network of how these oscillators are connected to each other, and depending upon what is the interaction strength, so how much they influence each other, and how much delay is between them receiving information from each other. So if that oscillator made some change, how much time it will take for me to get that information that there has been some change in that oscillator, and so I can tune myself. So based on these two factors, we can see emergence of these synchronization states and chimeric state, and how can we, if a system is synchronized, how can we induce a chimera state in that by inducing some delay in the system. So just basically showing things, just kind of giving like a very simple model for how introducing some delay in a very well-functioning system can lead to this kind of disorder emerging, a control disorder, to be honest. So yeah, I worked on that, and for during my PhD for a few months I worked on some trees.
Some trees
for forest. Yeah, that project is on hiatus. I am not working on it right now. Maybe in future, I don't know. But it was my supervisor's idea. He has this great paper on forest dynamics. So basically, if in a forest, all the trees, they are competing for resources, but they're also sharing resources. So through the roots of the trees. So what happens to the population of the trees if these resources fluctuate over time? Because the idea is the bigger trees have bigger canopy area, for example. So kind of shades the tree which are down, so it doesn't get enough sunlight. So for the smaller trees to live, the bigger tree has to die. And so they have this kind of weird dynamics that's going on. And so one can write a differential equation for it and solve it. And the results that, my supervisor saw was that it matches very well with the data they have from actual forests. So people, when they went to forest, measured the diameter of each tree and how many trees of a given diameter exist in a forest, etc. That distribution matches perfectly by looking at this competition between resources in those trees. So it's kind of, again, it's an example of, again, these small interacting systems, interacting units, resulting in this emergent behavior depending upon the conditions. And potentially it could be an idea to see how climate change will affect a given forest. So you can in the equation, you can fine tune, okay, my resources are now going down. Now what kind of change happens? We're going to make a prediction based on that and help people. But it's a range of things that I've been doing, but mostly focus on armed conflict right now and this last paper.
Yeah, and if I if I can stretch this into an analogy, get your thoughts. So there are forms of biological life that don't move. Trees, obviously an example. Barnacles in the sea, things like that. And so their dynamics, they're alive, they're interacting, they're sharing resources, they're also competing, but albeit without movement. So why is it that when you get species that actually move, that their ability to migrate, how does that actually change your thinking about the dynamics?
Dynamics in terms of?
Of, say, within the population. So what is it in a modeling sense, like when you're actually thinking about trying to understand it, what is it that differs between a population of trees from, say, a population of humans, or maybe less complex, like a buffalo or something?
Yeah, I mean, you say less complex, but it's very complex.
Right.
Yeah. That I get. I mean, yeah, the advantage of trees, or this whole approach that they did in the paper, was for sessile organisms, and sessile organisms are the ones which cannot move, and so fungi, trees, etc., etc. It's very easy to boil down all the main variables into some small number of variables. So the degree of freedom of these systems is less. It's not like low, like a physical system, but it's still less compared to if we have a buffalo or a mobile organism. Then the degree of freedom or the variables just explode. Now there's so much things that you need to. That being said, there are examples, like there are some good theories, like for example, the famous predator-prey model from complex systems. So if you have a population of predator and prey, depending upon the ratio of their initial demography, you can kind of tell what would be the evolution of this population, whether they will oscillate, whether one of them will die out, whether the prey dies out, or predator dies out, etc. You can write an exact equation for it. You can solve it, and you see what happens. But again, that predicting death and just population number is, in this sense, is easier than predicting other things. Like, I mean, if I don't know what else in a buffalo you can predict.
Right. There aren't emergent, aspects
I mean, I'm sure there are. There are these in sheeps. There are these emergent patterns that they show while grazing from top. So there are, again, if you can write equations for it, you can kind of get that too. So it comes in the pedestrian dynamics thing that also humans, like all the cities, I'm sure they have some guy in all cities trying to do this calculation and see how to navigate the crowd in good functioning cities. Not
right.
Same with traffic, like individual. There's every car is making its own. Every driver is making their own decision. They have some set constraints, but and then they have this emergent dynamics, which are of some fixed types, and you can kind of classify them. And if something happens in the system, you can kind of drive the system towards some other kind of dynamics. But again, these things are still easier than looking, like modeling conflict, let's say. Like in a population of buffalo, how would you model conflict?
Right.
That's very difficult in my opinion. But I don't know, maybe if the field reaches there. Right? This is still the beginning, right? So
yeah, so I guess that brings me directly to the next question, which is, where do you see the field going in a broader sense?
The complex systems?
Yeah.
Oh wow, this is I'm not the right person to ask this question, because since the complex systems or complexity science as a field itself, by design, it's very interdisciplinary. So people from every field have their own opinion of, first, how to study complex systems, and then where should the complex system go, in which direction, methods wise, or the kind of questions we should tackle and the kind of questions we need to ask. So if you ask some physicists, the physicists have a very different priority in questions and the answers they want to get to, let's say, some economist who's in complex systems. But in general, I think, in my opinion, just understanding any complex system like any system with interacting elements and the emergent phenomena, understanding it and hopefully modeling it in a way that we can inspire some kind of on-ground policy decisions based on it is something I want to see. I want to. A lot of policy, even in the policy sphere, a lot of decisions are made on very linear models. Most of the economic models, macroeconomic models, are very linear in nature. There's some regression going on, which is good, which is very nice, informative. But I think it's time that we move beyond that. And we actually, instead of removing all this complexity and just boiling down to some few variables and just doing a linear, assuming everything moves linearly and try to get some output out of it, try to bring in some of this complexity and see what you can get out of it. So I think that's one direction I want to go in. So, for example, by doing all this work in the armed conflicts, that's what I would expect, that I can talk to some experts in armed conflict itself and try to inspire them to kind of think in this complex systems way first, and then try to see what kind of questions we can answer together. For example, this whole, you cannot predict conflicts or in conflict intensity just by looking at data sets. In the field, people are still very hard at, like, they're just pushing at that and trying to build. I think a lot of people think that what we're lacking is a bad model. But I think it's either we don't have enough data, like good enough data to predict it, or the system itself has this property that it cannot be predicted by this. So there's no point in doing that. So trying to convey this to other kind of fields and be like a complement to that, never replacing any field, can never replace qualitative work or on-ground work, but complement this with this. And I think that's what I would like to see. The complex systems that are kind of research I do go, but then there are other people who just want to stay in the theoretical front, which is also fine. I'm very diplomatic in this, but as I said, I'm not the right person to answer this question.
Yes, I guess why you're kind of touching on it, but why are you doing the work that you're doing?
I mean, as I said, I mean, how personal do you want this answer
I mean,
to be?
as personal as you want to get. Yeah.
I mean, so in India, I'm coming from an institute which is like a really good tech institute. It's like IITs. It's kind of well known, and you learn a lot of skills there, and really nice skills. How you use those skills is now on you. And from what I saw, most people choose to go in the finance or go in like this kind of, the triangle of Bermuda Triangle of
Shame.
I didn't say it.
I used to be in
Your
finance, so
podcast.
I'll say it.
Okay.
Yeah.
And for me, it was always like if I've gotten these skills, if I've gotten this understanding, I should use it for something which is more like good. I was always interested in physics. As a physicist, you are interested in knowing whatever you're studying deep down in the most fundamental level, and so that's why I chose to come into complex systems, where I get to use those skills to do some like good research, which can be used on ground, a lot of data-driven research, but also in this pursuit, I get to understand the system into a very fundamental level. So these questions, these more broad questions about this emergence of irregularities or these patterns in conflict, why is this happening? How does one affect the other? Like how does one process or one phenomena affect the other? Like democratic backsliding, conflict, things like that. So yeah, I mean, all this criteria that I had for what kind of work I want to do, complex systems kind of fulfills that, and so that's why I'm doing. But in the end, I would say I'm not that interested in the fully abstract side. To do some modeling, do some theory, but then I would like to apply it to see if in the community it has some kind of impact, or in the society somehow. So yeah, so that's I think that's why I'm doing this.
Yeah, amazing.
What about you? Can I ask a question to you?
Yeah, why not?
Why are you doing this?
Yeah, it's a very similar thing of trying to do something that actually appreciates humanity, appreciates values cognition. Obviously, I study cognition itself, but I also see cognition as something extremely beautiful, something extremely profound. Every time we try to look outside of it, there's a bias of being, a biological system on Earth. Yeah. But, because I don't intuit any meaning out there in the universe, I decided to just put all of my energy of meaning into just saying, well, then biological life is the thing I'm putting meaning into. Yeah. And it seems like, understanding cognition, if I also have a very sort of similar hope as you, is that some of the work can be directly engaging with ideas that we're trying to engage with now, of societal problems, and then eventually try to do something like inform policy. Mm-hmm. And that's also one of the reasons why I do this and the podcast, is to try to get people on who are passionate about what they do and who also have a vision of putting that to society and saying, look, when we look at these problems with everything we've got, this is what we see, and hopefully it's useful.
Yeah. Well, we have very similar ideas then. That's good.
Is there anything else you'd want to add that we could cover?
From my side, it's great to be here. I would say that. If you can talk about your latest research, I would be happy to hear. But
we'll chat about that offline then.
Okay. Perfect. I
don't want to, but yeah, then hopefully I can get you back on as a co-host for some other folks, because this was really great.
Oh, thank you for having me.
Yeah, thank you so much, Niraj.